Okay, hi all. Today we're going to talk about parallelograms. So parallelograms are one of those quadrilaterals that we spoke about yesterday, but they have particular features of interest to us. So the first thing about parallelograms is that opposite sides in a parallelogram are parallel to each other. So we can do this kind of a symbol to show that the opposite sides are parallel to each other. And if they're parallel, then these two sides are also parallel to each other. So that's the first thing. The second thing with parallelograms is that opposite sides are equal in length. So this length is equal to this length is equal to this length. And lastly, I suppose, importantly, is that the opposite angles in a parallelogram are equal in measure. If we look at this angle here, we can see that it's slightly more than 90 degrees, so maybe it's about 95 or 100 degrees. So it's an obtuse angle. And up here we can see as well that this angle is also greater than 90 degrees, just slightly over 90 degrees, and it's also an obtuse angle. So even though that's not mathematically sound to say they both look obtuse, I can tell you they're definitely equal in measure, but intuitively I think we would say that it seems right that they would be equal in measure. Also, we can see up here we've got this acute angle, and it's slightly less than 90 degrees, I would say, so maybe about 80 degrees. And this angle here is equal in measure to this angle over here, which we can see is also slightly less than 90 degrees, so it's also an acute angle. Now we can prove that these angles, these opposite angles, are equal in measure at a later time, but for now, for the exercises we'll be doing, we can just take it to be true. So that's the first thing. So let's look at some exercises we might do in regards to parallelograms. So find the value of x, y, and z in this parallelogram. So 80 degrees and then x, y, and z. So they're giving us one of the angles. So quite straightforward, we can say that, well, if that's 80 and opposite angles are equal in measure, then y must also be 80. So y is equal to 80 degrees. Then we can use our rule about quadrilaterals. Well, this is one way we can do it. We can use our rule about quadrilaterals that all four angles in a quadrilateral must sum to 360 degrees. So we've got 80 and 80, which is 160. So 80 plus 80 is equal to 160. We know that all four of them must add up to 360. So if we take the 160 we have so far from 360, we're left with 200 degrees. So this x and this z must equal together, they must equal 200 degrees. And we know from what we discussed above that they have to be the same size. So we can divide our 200 degrees by 2, and this will be 100 and that will be 100. So x is equal to 100 degrees and z is equal to 100 degrees. So that's the first one. Also, there's something that we need to be conscious of anytime we're dealing with parallelograms. Because we're dealing with parallel sides, we always have this situation that we studied already about two parallel lines and a transversal. So if you take, for instance, these two parallel lines here, this one and this one, if we were to just extend that a little bit here and extend up here and extend this here and forget about over on this side, ignore that, we could probably see that we've got a parallel line, and a transversal. So when we have parallelograms, we're often asked to find things like this angle or that angle or this angle, in which case it would be no problem. This would be vertically opposite, it would be 80 degrees. We could have said, when we were finding x, instead of finding z first and using our 360 degrees, we could have said that, well, these are interior angles when we have two parallel lines and a transversal. So we could have said that interior angles sum to 180. So 80 plus this sums to 180. We could have gotten straight to x being equal to 100 degrees. We could also, if we wanted to find this, we could say it must be 80 degrees because these are alternate angles. They're on opposite sides of the transversal, but they're in between the two parallel lines. We could have said it was 80 also, because if this is 80, that's the corresponding angle here, so it must also be equal to 80. Corresponding angles are equal. So we could find any number of different angles using the fact that we've got two parallel lines and a transversal. But also, equally, I mean, if we turn our page sideways here and we use our other two sides of this parallelogram, we also have two parallel lines and a transversal if we want to use this. So let's just extend this out. We've already extended that and that. So ignoring everything over here, then you have again two parallel lines and a transversal. So all the same rules apply that you had with parallel lines and transversals. If this is 100, then this must be 80 because interior angles are equal. If that's 100, this must be 100 because they are alternate angles, opposite sides of the transversal and between the two parallel lines. If this is 100, this has to be 100, doesn't it? Because they're corresponding angles, or because this and this are vertically opposite angles. So always be on the lookout when we're talking about parallelograms for that two parallel lines and a transversal, because it exists in a number of areas within this parallelogram drawing. So let's look at our second example of a question. Again, it's the same, find the value of x, y, and z, but this time with a different parallelogram. So here we have, we've been given this 70-degree angle, this 30-degree angle, and we're asked to find the angle here, and the angle here. Now, what I should have done was made it explicit from my drawing that this is a parallelogram by putting in these symbols for parallel sides. So this is a parallelogram, and again what we're going to do in order to find x and y is we're going to use our knowledge of parallel lines and a transversal. So excuse me, if we first of all forget about this side here and forget about this side here, and we just concentrate on this line and this line, they're two parallel lines, and then we extend this just to make it, you don't have to extend it of course, but it's just to make it easier for you to see from when you were studying parallel lines and transversals. So again, if we sort of pretend that doesn't exist and this doesn't exist, we can see that we've got this angle and this angle, which are on opposite sides of the transversal, and they're in between the two parallel lines. They're alternate angles, and we know that alternate angles are equal in measure, so this must be 30 degrees. And the same goes if we were to turn our parallelogram around like this, and we were to extend this line, we'll say, and this line, and if we were to pretend that this doesn't exist, this side of the parallelogram and this side of the parallelogram doesn't exist. So if we just had one line and a parallel line and a transversal going across the two of them, well then we can see we've got this 70 degrees and this angle y are alternate angles because they're on opposite sides of the transversal and they're in between the two parallel lines that we're using here, this one and this one. So they're alternate angles. So y is 70 degrees. I'm just going to put that in here. 70 degrees. And then lastly, if we want to get z, well, there's only any number of ways we can do this. I think the easiest way is probably to use the angles in a triangle. So we've got a triangle here. The angles in a triangle must sum to 180 degrees. So 70 and 30 is 100. So z must be 80 degrees. So x equal to 30 degrees, y equal to 70 degrees, and z equal to 80 degrees.